C is very flexible and well-established programming language, thus making it the mother of all programming language. Many essential libraries, firmwares and operating systems are implemented using C. For example, in Linux, more than 85% of job is done using C. Getting into any tech giants like Google, Amazon, Facebook or Microsoft, you need to have a solid knowledge on data structures, and that's what we are going to learn in this session. Hi, welcome to this session on data structures using C. In this session, we are going to cover C programming language, data structures, arrays, linked list, stacks, and queues. Then we will talk about binary tree, binary search tree, heaps. Then we will talk about hashing and try to implement hash table. And finally, we are going to conclude our session with graphs. Let's talk about C programming language. So C programming language was designed by Dennis Ritchie in 1972, right? If you want to save some file written in C programming language, you have to use an extension of .h or .c, right? So why was it developed? It was developed to make assembly language work much easier. What do you mean by that? Basically, if something is written in an assembly language, if you might have used some time, maybe somewhere you have seen its code, it is similar to a low-level language, right? It is, if I explain it in a naive way, right, it is similar to our machine language, that is zeros and ones, except it is written in words, right? We have words to write an assembly language. So you can see if I'm comparing it with a machine language, right? So it is not a machine language, it is a low level language basically. Yeah, if I'm comparing it with that, so it has to be, or it is much complex, right? So instead of using assembly language, what Dennis Ritchie did, he designed a C programming language, which is a high level language. So he designed it in 1972, right? So it is a procedural language. What do you mean by that? You have to follow some sequence of steps to get the desired output, right? So it is much faster. So I have read somewhere it. So, and I have tried it myself also. So if you try a simple program, maybe some addition of two numbers or any simple program, maybe a linear search, right? So if you try to do it in 5 different languages, maybe C, C++, Java, Go, and maybe JavaScript. If you try to do it, and if you try to execute all those, and Python as well, Python takes much time. So if you try to execute those, all the a simple program written in all those languages, right? So you will see that C performs much better. I'm talking about simple programs, though there is a huge difference between C programming and all those object-oriented languages, right? But I'm talking about some simple program. We're not discussing or we're not dealing with those object-oriented features, right? So yeah, C works much faster, okay? It handles a low-level activity much better. These are certain points that I have, basically we are dealing with data structures, but these are certain points that you should know. What do you mean by this low-level activity, right? So basically, if you're trying to store something, or if you're trying to allocate memory and you're trying to free that memory, you are responsible for that using malloc and free, right? So there is no garbage collector in C, right? So it handles that low level activity. You see that handling those, allocating those memories and using free to free the memory, right? You are responsible for that. So that is what this means. There are other things that this line means, but I'm looking at bigger picture, right? So you are responsible for this, okay? So some of the applications or operating systems that are written in it are Unix operating system, RDBMs, MySQL. Both of these are written in C, okay? Now let's talk about data structures. So if you see, there are 2 words in it, right? Data and structure. What do you mean by data? Well, something that is related to information or facts or something like that, right? So data, information, or you want to store that information, but there should be some structure to it, right? Wherein you store this data, how you store it data. So that's wherein data structure comes into picture, right? It is a way to arrange data in computers, okay? some of the data structures that we are going to study in this lecture are linear data structures and non-linear data structures. What do you mean by that? So if something is stored in a linear fashion, that is in sequence, right? There is a order to it, right? So those data structures are called linear, and there is an order in hierarchical data structures as well. If we talk about non-linear data structures, right, trees, graphs, these are non-linear data structures, and linear data structures are arrays, linked lists, stacks, queues. These are all linear data structures. Okay, we're going to study about them one by one. You don't have to worry right now. So that's what this session is all about. Okay, so these are the list of data structures we are going to cover today, right? So the first is arrays, then linked list, stacks, queues, binary tree, binary search tree, heap, hashing, and graphs. So let's get started. So arrays are linear data structures. What do you mean by that? If you want to store something, it will be in sequence, right? There is 5, then there is 2, then there is 3. You want to store these data structures. But what do you mean by contiguous memory allocation? Basically, if you're trying to store an element which is of type, the data type of that element is integer, right? So I'm talking about 32-bit operating system here. Okay, the size of int is 2. If it isn't 64, it is what, 4, right? Yes. If you want to store those data in your memory, right? So if 5 is stored in, let's talk about some arbitrary address, right? It is 100. So talking about 32-bit operating system, int will be of 2 bytes. So the next data that will be, the address given to it will be 102. Okay, 100, 102, 104. So there is a sequence to it, right? You see, so that's what I mean by array stored in a contiguous memory allocation. If there is no contiguous memory allocation of 3 wherein I can store this data, so it can't store it, right? This is, maybe there are 3 addresses present in a memory, but you can't store it. Not if they are jumbled, or if they are somewhere else, you can't store them. So it has to be contiguous memory allocations. Okay, so can we access randomly in arrays? Can we access elements randomly in array? So yes, you can access elements randomly using its index. As we all know, name of the array depicts its base address. Okay, as we all know, base of the address is represented as name of the array. Okay, so there is name associated to each array, so it represents its base address. So yes, we can access elements randomly using its index. We will check all those details. I mean, how do we declare, how we initialize, and then I will give you a bonus question as well related to arrays, wherein I will teach you also how efficiently we can solve problems, right? So can we store different data types of elements? That means, can we store float, can we store int, and can we store a character in a single array, in the same array? No, we can't. It is homogeneous. That is, we have to store similar elements. Okay, what is the syntax of array? Okay, first we have to give a data type, right? I was talking about earlier a 32-bit operating system wherein size of int is 2, then there will be 102, then there will be 104, right? So there is a data type associated with array, right? So yes, we have to, whenever we are declaring an array, we have to give its data type. For example, int, then its name. As I already taught you, the name is very important because it represents its base address, right? So yeah, name is important. So int arr, and then we have to give its size, right? It's not dynamic, it has to be static, and we have to give a size to it. Maybe size can be omitted, wherein we are declaring and initializing an array in the same line as I have told you, you can omit size when you're trying to declare and initialize an array in the same line. Okay, wherein I have given an example that data type var name, and then brackets, that's the square brackets are empty, and then as then I have written element 1, element 2, element 3, and element 4. There is no size, right? So why there is not any size? Because I am declaring and initializing at once. Okay, so yeah, let's go. What are the advantages of arrays? Okay, random access. I can access elements randomly, right? It's easy for sorting and iterating, right? I can use a single loop to iterate through an array, right? Replacement of multiple values. What do you mean by this thing? So someday I told you that please store 50 students or 50 roll numbers. How would you do that? Do you use int x, int y, int z, int 1, int 2, int 3 written in words, I mean, not letter, not a numeric one. You can't. That is not a right way to declare a variable, right? So you will use int one then along the way to 50, right? Is that an efficient way? No, right? So you can use an array of size 50 that will do the thing, right? Yeah, so this is an advantage, one of the advantages, right? So what are the disadvantages? That this seems to be a thing, right? You have to fix a size, right? If you're declared an array of 50, then you're trying to store 51 elements. Can you do that? No, right? Difficult to insert and delete. Why it's difficult? Because if you're trying to delete something, maybe you can't delete an array size, right? So if I told you now the god forbidden 20th student has died, so you have to remove it. Can you remove it? No, you have to swap all the elements from 20 or maybe or 20. You have to swap all the elements to its right one by one position, right? So it is difficult to delete and insert an element. So now I told you a 20 is again alive, magic, right? Yeah, so I told you yeah, he was lying or he was saying something. Someday he came back, no, or any other student came, right? He's dead, right? He can't come back, and I have to give the same roll number to him, 20 roll number, right? So how would you do that? Again, we have to reswap the elements by one position if I'm having a size of 50, right? So there is a size of 50, so I can. If my array is full and I'm storing all the 50 students in it, I can't. Okay. And the one more thing which I told you earlier, that it needs to be contiguous, right? So if there are chunks of memories available but they are not what I want as a contiguous memory allocation which I require to store an array, we can't use that. We can't store an array elements, right? Its capacity is more than its occupancy is less. So yeah, there is another point which I want to discuss also. So what if I told you I have 50 students but only 20 came? Okay, you declare an array of 50, but you are storing only 20 elements in it. So yeah, you are wasting some part of your memory, right? So this is the disadvantage of having a fixed size, right? So yeah, what are the applications of arrays? For storing information in linear fashion, yeah, you can store elements in a linear fashion, right? Yeah, the other application is that it is suitable for applications that requires frequent searching. There is something called binary search and linear search. Wherein we use these algorithms to search something in an array. So let's get going. Demonstration of array. So how we declare it, how we initialize it, how we print elements in an array. That is what is written in this. So I believe that you are familiar with the language, so I don't have to discuss these things, right? Hash include and studio.h and int main. I don't have to discuss these things, so I will get to the business end, right? So to declare an array, you have to use int in front, then the name of the array, then the size. Okay, so then we loop around to insert each element in an array using an ampersand sign, that is to get the address and then store an element on that position, right? So yeah, then we loop around again to store to fetch the values from that address. You see, we are not using that star sign, right? Why we are not using? We are fetching something from maybe this is not a pointer, but you are dealing with addresses, right? So that's what I was saying, that this roll number depicts its base address. Okay, we're going to that base address and we're saying that at 0th index please fetch that element. Okay, so that's how we deal with arrays. Okay, so you see that scanf and printf, Why these functions are not declared? Because we are using the library studio.h. Okay, so now the arrays are completed. So now I was talking about one bonus question, right? I will try to include a bonus question after every module or every data structure that we cover. Okay, so the question is, I'm using first I will tell you what I'm using. Dev C++ to store for executing my C code. You can use your editor or you can use any IDE. We have different IDEs on Lead Code, Geek or Geeks, right? Or if you find this question on any of these competitive programming websites, you can do it. Okay, so the question is, you have an array, right? In that array, every element is repeated twice. Okay, every element is repeated twice. So if there is an element 1, it will be repeated once. Okay, 2, it will be repeated twice. It will, if there is 3, it will be repeated twice. Okay, so every element is repeated twice except 1. For example, let's say 4 is not repeated. Then there is 5 is repeated. So our problem is that we have to find this 4. Okay, right? This is highlighted. So every element is repeated twice except 1. So we have to find that element. So how we would do this? Think about it. Pause the video. Think about it. Okay, then I will show you the solution. Now let's get to the solution. Okay, so you have different solutions. Maybe I hope that you have paused the video and tried yourself, and let's go to the solution. So I will use, there are many ways you can solve this question, right? I will use the most optimized or most optimal solution. I won't I won't deal with those solutions which are not optimal. I will straight away and go into the optimal solution. Okay, so first we will include the library, yeah, then int main. Okay, then I will declare an array and initialize it in the same line. Okay, so int arr. Okay, so every element is written twice. 1 2 3, then 2 3, then 1, then 4, then 5, then 5, then 6, then 6. Okay, so every element is repeated twice. So what I'm going to do here, so I believe you have heard about bitwise operators. Bitwise operator. So have you heard about XOR operator, written like this, caret sign? Okay, have you heard about this? So what does this do? So 1 XOR 1, what will be the result? It will be 0, right? And if we are doing 0 XOR 0, that means I'm talking about the number. Okay, 0 XOR 0, it will again be 0, right? So we know that if same elements are XORed with itself, say two elements which are same that are XORed, they will give a 0, right? So if they are different, then we will calculate it. For example, if 4 is XORed with 5, right? How we will do it? We will calculate what 100 is the binary representation of 4, right? 100, right? I don't want to go in details how I calculated this. I believe you all will be knowing it, right? And the binary representation of 5 is 105, right? So 1 and 1 will give me 0, right? 0 and 0 will give me 0, and 0 and 1 will give me 1, right? So it will be 001, right? So yeah, then this is the result, right? So we are going to use something similar to this. How we use it is the question, right? So we have the array. I will loop around it, right? I will use a for loop. Int I equal to 0, I less than what? The size of the array is 1 2 3 4 5 6 7 8 9 and 10. These 10 elements, 1 2 3 4 5 6 7 8 9 10 11 elements are there, right? So I will use less than 11 and I plus plus. Okay, So how will we get the result, right? I will use some variable here for storing the result. Okay, starting is 0. So if I do something like this, result is equivalent to result XOR AR out of I, what, and this will give me my result. Are you confused, guys? If yes, I will explain. So anyways, I'm going to explain this. Okay, so this will give me the result. Please don't compare it with your solutions. Maybe your solutions are giving the right answer, but they will be not optimized. I have solved it in a linear time. The time complexity of this is verse time complexity big O of n, right? So every element, if my element which is my answer is at the end, that means 1 is at the end of the array, or I am traversing anyways to the end of the array, right? There are 11 elements and I am traversing 11 times. So yes, it is solved in linear times. Now the question is how. So first try to print this, printf, right? Then %d, comma, let's do this again. Okay, then %d, and then our result. So what should be the result? So let's first save this file, and yes, let's try to save this file, and now try to execute it. Do the compile and run. Hash include studio hash is missing, right? Solve it, save it again, and run it. So 4 is the answer, right? 4 is the only element which is not repeated, right? So there won't be any, you might be confused that if other number is repeated or other number is missing. No, the question is very specific that every element is repeated twice except one. We have to find that one element. Okay, so we found our answer. Now let's try to debug it, right? This is solved in linear time. You all guys get it, right? So how we got to the result? So 1 is XORed with 1. Let's go with the array. So if I'm talking about if I XORed, say this way, 1 is XORed with 1, then that will be XORed with something else, then 2 is XORed with 2, right? Then this will be XORed with something else, then 3 will be XORed with 3, and this will be XORed with something else, then there is 5 XORed with 5, right? Similarly 6 is XORed with 6, and then it's XORed with 1. No, 4, right? 4 is missing. So there are 11 elements, right? What will be the output of this XOR? Think about it. It will be 0, right? What will be this? 0, this 0, this 0, this 0. So 0 XORed with 0, 0 XORed with 0, 0 XORed with 0 will be 0, right? So it will be 0. So what will be the result of this? So 0, 0, 0. I'm not considering all those zeros. I'm only considering that many bits which I need. Okay. So yeah, this will be XORed with this, right? So what will be the result? 4, right? So that's how we got to the answer. That's why that's how we are executing this. Okay. So yeah, that will be it, right? So okay, cool. So we have done this question. Please compare it with your question and think about the complexity that you used or you try to solve this problem. If someone is able to do this problem using same approach, well done. If someone is not, no need to worry, right? These things come with time. Okay, you don't have to worry about anything. So we are done with arrays. Okay.
Now let's talk about linked list. As we saw earlier, there were many problems associated with arrays, right? We have to give size was static. We can't store elements if the memory is not available in a sequence, right? If the chunks of memories are available here and there, we can't store our elements, right? So these problems were solved by linked list. There were some similarities, or there are some similarities between arrays and linked list, right? Both of these are linear data structures, right? Both of them can store homogeneous elements, that is similar elements, right? Elements can be stored as per memory availability. This is the key point here. If memory chunks are available here and there, with the help of link, as the name suggests, we can store our elements. Okay, we can access elements in a linear fashion only. There's a bit difference between the access, how we access elements in arrays and in linked list, that how we access the elements. We have to traverse through the linked list if we want to access any element. Say for example, we want to access element which is present at index 5. In arrays, we can simply write that index, right? Index -1, we can get that index, right? But in linked list, there is no index, right? We have to traverse to that element. Okay, so there is easy insertion and deletion. There is a difference again between arrays and linked list in a way that if we want to insert or delete an element, we need to swap elements in arrays, right? But in linked list, we can do that easily by changing the links. For example, if we want to insert some node, right, we just break the link from that node which are earlier connected with each other. Okay, we can easily connect that node with the other node and the other node with that node. Okay, I will show you later. Okay, don't get confused. But there is one key point here, right? Always we have a node which is called a head node, and we don't change it no matter what. Okay, we keep the head node. If we, for example, somehow by mistake change that head node, we will get an updated list. Okay, it might be some elements will be included in it, or it might be the case wherein we lose some elements or nodes. Okay, let's go ahead and talk about advantages and disadvantages. So what are the advantages? Dynamic insights, right? No wastage of capacity, as we don't have to give a size, so that if we somehow used less elements in arrays as compared to arrays wherein if we gave a size of 5, right, and then we only stored 2 elements in it, but the memory is wasted, right? That is not the case here. Okay, easy insertion and deletion. Only a single link needs to be manipulated. Efficient memory allocation, right? If chunks of memories are available here and there, we can easily insert our elements, right? We can still allocate memory to our elements, right? What are the disadvantages? Head node is key. If it is lost, linked list is lost. No random access. As explained earlier, we have to traverse. So what are the applications? If memory is limited, use linked list. Okay, if the application that requires frequent insertion and deletion as compared to arrays, we need to swap, but in linked list we don't need to swap, so we can use linked list there. Let's see the demonstration of linked list. So why do we include standard stdlib.h, right? Why do we include this file, this library? Okay, because we are using a function called malloc here. Okay, so for that, to use that function, we need to include this file studio.h. Why do we include this file? Because we are using printf and scanf statements, right? So these functions, we don't declare these functions, we just include the libraries. What is the skeleton of node, right? The structure is defined here of type node, right, wherein there are 2 elements. One is data and another is the address part, which is of type node. Okay, the pointer. Then how would we traverse. Okay, here we have given a display function, right, which takes argument as a node, right, a pointer of type node. Okay, so how would we traverse? First we check if the element, the node that we send, if it's null, we are sending a head node, right? With the help of head node we can traverse to the end of the linked list. So first we check if that node is null, that means there is no list. Okay, then how are we going to traverse it? Okay, then we just print the data in the linked list and then we shift our link to the next node. Okay, that is what we do. If we want to access any element in a structure, how would we do it? We just draw this arrow, right? Okay, so this is how we traverse. Let's go ahead and quickly go into the details. Okay, first we have declared a node, a pointer to a node which is called head to null. Then there are two temporary nodes or temporary variables of pointer type. Then we have declared two pointers. Okay, temporary pointer second and third. Okay, how we allocate memory? We allocate memory with the help of malloc function. It takes argument as a size of the node and then we typecast it to the node. Similarly, okay, similarly those two second and third have been given a memory. Okay, then how we assign our values? Okay, we just do head arrow data, right? Data is equal to 10, and then we assign data to second node which is 20, then third node which is 30. Okay, how we link nodes? For example, head node is linked to second, so how would we do that? So what we do, please go and whatever is in the second node's address or whatever is the address of second node, please put that address in head's next. Okay, so there is a link between head and the second node, then second node and the third node, and then third node's next contains null because our list contains only three elements, that is head, second and third, that is 10, 20 and 30 with data. And then we call a display function which is in which we pass our head. With the help of head we traverse through the linked list and finally we print out our output as 10, 20 and 30. Okay, now comes the time wherein I give you a bonus question. Okay, so the question is, we have to find the middle element in a linked list. For example, you have a list of 1 2 3 4 5, you have to find the middle element. What is the middle element? 3, right? Go ahead and give it a try. Pause the video and then we will start with the solution. Okay, so now let's quickly go ahead and check the solution of this question. Okay, there is one key point that you have to notice. Okay, what is it? So if the list contains, for example, these elements, okay, I'm writing it here, 1 2 3 4 5 6. Okay, so there are 6 elements. How would you know if the element 4 or 5 is the middle one? So it will be defined in the question. We will go accordingly. For example, in my case, I'm defining that this is the middle element 5. Okay, though you have a choice between 4 and 5, it will be defined in the question. Okay, so if the 7 is not present, then it's easy, right? 4 is the middle element, it can be seen, right? So it will be defined in the question. Okay, now I haven't written the entire code. Okay, I have just given the function which is giving me the output as the middle element. So I have passed the head node to this function. Then I define two pointers, slow and fast, to head. I have assigned them to head. Okay, for example, if one is the head here, so all these three elements, that is head, slow and fast, will be pointing to 1. Okay, so let's go ahead. First we will check if the head is not null, right? There is no list, and how will we find the middle element, right? Makes sense? Okay, so this is for that. If this is not present, then we don't do anything. Okay, then if head node is not null, right, in the case as we are defining for this problem written here. Okay, let's forget about this, what I have done here. Let's first check out what I have done. What is the approach? So I'm using two pointers, as you might have heard about this famous saying that rabbit and tortoise thing, right? Rabbit goes fast and tortoise moves slowly. So what here, fast is moving 2 pointers, okay, and this is moving single time. and this is moving twice. So this is the concept here. I'm using two pointers, one is pointing to the next and one is pointing to the next. Okay, for example, now for the starting node, what I have done, so please assign fast next. So fast will be pointing now to 4, right? So at starting it will be at 1, so next is 3 and next is 4, so it will be pointing to 4. Basically it will be pointing to the address that is present at that is having a data of 4. So now right now I am just for the sake of simplicity I am using 4 as its value. Okay, so where will be slow will be at 3. Okay, so let's quickly go ahead. Is fast null? No, it is not null. What is fast? Fast is 4. And is fast next null? No. What is fast next? 4's next is 5. So both these conditions are true. There is an AND statement, AND operator used. Okay, so both these statements have to be true. So now what happens? So now 4 will be pointing to 4's next, that is 6. 4 will be at 6, right? So now fast will be at 6 and slow will be at 4, right? Then we move ahead and check the condition. Is fast null? No, it is 6. Okay, and then is fast next null? Yes, it is. We don't have any element after 6, so this becomes null. So can we execute this while loop? No, we will go out of this while loop and print whatever is in the slows data part. What is in the slows data part? That is 4. So is 4 our middle element? Yes, it is. Now the case comes when we have even element 7, for example. Now let's continue where we exited our while loop. So is fast next null? No, it is not. It is 7. So this will be pointed to 7's next, which is null. So fast will be null here and slow will move ahead to 5. Now we will again execute this. Is fast null? Yes, it is. So are we executing this part? No, this is the property of AND operator. If this is true, then only we will go to this condition. Okay, so this will exit the loop and we will print whatever is in the slows data part. So what is it? 5. So I told you earlier that I am using the example that in my question it is given that 5 is the middle element whenever we are having even elements in a linked list. So you got the point. Please compare it to your problem, what you have written or whatever you have tried. So you compare it and then check it. Okay, now let's talk about stack. Stack is also a linear data structure, but there is one property that it has to follow. Let me take an example first. If we have a stack of plates or stack of chairs, how can you remove? Can you remove the last element, last plate? No. Or the last chair? No. Whatever is at the top, you can remove only that. That is, whatever came in the last was removed first. So it follows LIFO structure kind of a thing, right? Last in, first out. Only the top element is available to be accessed. You can't access the last chair, right? Or the last plate. You have to access, you get the access from the top. Okay, you can only remove the top of the element. Okay, insertion and deletion takes place from the top as obvious, right? It is obvious that if we can only remove from the top and only insert from the top, whatever is in the top, we get to remove only that. There are 4 major operations associated with stack. Push, that is push the element or insert the element at top of the stack. Pop removes the element from top of the stack. Is empty checks. If the stack is empty, then it returns true, else it will return false. We will use this function very frequently in our programs. Okay, the stack is a very important data structure. Then there is another operation that we have in stacks, that is peek. So what do you mean by peek? Peek is how it is different from pop. Basically both these pop and peek execute in a similar fashion. Only thing is that pop will remove that element and peek will not. Peek will just check whatever is in the top, it will give it to you. Okay, all these operation works in constant time. As we will use one variable top, which will be with which we can get the access of the top element, and we will use that element only to push, pop and check if it is empty, and peek with the help of that variable top, which will be defined. Okay, so all these operations will be of constant time, will take constant time. Okay, now let's talk about advantages and disadvantages of stack. So stack advantages, that stack maintains data in LIFO manner, right? We have explained it earlier what a LIFO means. The last element is readily available for use, right? Self-explanatory this line, right? All the operations take constant amount of time. Now let's talk about disadvantages. Okay, what is manipulation is restricted, right? We only get to choose the element, or we only get the access of the top of the element which is present in the stack, right? There is no much flexibility in stacks, right? We are stuck with this thing that we have to access only the top of the element, or we have to remove element from the top, we can insert element from the top, so there is not much flexibility. So applications is whenever we recursively do a program, or we are using recursion in our program, inside this recursion we are using stack as a data structure. Okay, parsing is another application. Browsers, right? In a browser, if you type something in a Google, then you move to that link, then in that link you move to different link. So if you do back, which is present in the tab section, right? If you press back, then it will go back to the previous link, then back, then it will go to the previous link. So it maintains a stack there, right? In editors you might have seen undo, right? Undo and redo operations, those are also using stack, right? Let's move ahead and try to demonstrate how the stack works. I have used array implementation. Similarly, you can use linked list implementation as well. That is a small assignment for you guys, to implement stack using linked list. I have explained the linked list. Make it a static one. You don't have to do fancy stuff. Just make it a static one and try to implement stack using linked list. Okay, so here we have defined some there are 3 libraries that we need, right? Standard lib for malloc, studio for printf, and scanf. Now let's go ahead and check the skeleton of the stack. So stack, in here we are using arrays, so we have to define a size, right? Size of the array that is going to be, right? And there is a pointer which is pointing, there is an integer array as an element, right? And there is another element which is top needs to be there, because this is going to help us a lot. Okay, how would we create a stack? Basically, for creating a stack we need a structure that is there. We use that structure because at the end we are returning the stack, which is a pointer. So a pointer type of pointer is returned from this create stack operation. So there is an argument unsigned size, right, which will help us to allocate memory to the array. If you can check the statement which is just written above the return statement, that we are allocating memory with the help of this size that has been given to us as an argument. We are using that size and then we are typecasting it to an integer, right? We have an integer array. Then there is top, which is at present at -1. That means there are no elements in the stack right now. And then we assign size, which is present to the size which is associated with the stack. Okay, and also we are allocating memory to our stack. Okay, these are the operations that we need to follow. Then after that there is one other function that I have written here, that is to check if the stack is full or not, right? If the top of the stack is equal to the size -1, right? We are using arrays, so index -1 will be the last element that will be present in the stack. So if that size and the top of the stack are at same position, that means our stack is full. Let's go ahead and check other functions. Is empty, right? If the top of the stack is at -1, that means we don't have any elements in the stack, right? So the how we can add an item to a stack. So this is a push function, then there is pop, then there is peek. Okay, so how we gonna push it? So we need to check two conditions, right? The overflow condition and the underflow condition. What do you mean by overflow? For example, we are talking here about arrays. So if an array size is 5, that means we can include 5 elements, right? So we need to check this condition that we are not including the 6th element in the stack, right? That is what is written here, the if condition. So is full function is checking that if we can insert an element in the stack, then we simply add element to the index, to that index, with the help of top. It is a pre-increment. So first we increment, because it was at -1, so we first increment the top, then assign value to it, right? Similarly, the next time we first increment that, then assign value. So this is the push function. How we remove element from the stack? Basically, we check the underflow condition here. If the stack is at -1, that is, we can't remove any element, right? There are no elements, so we need to check that condition, that is the underflow condition. Then we simply remove element which is present at top, and then we decrement. It is post decrement. Then that means first we remove that element, then we decrement our top. Okay, this is how we do it. And then finally we check for the peek function. So peek just returns whatever is at the top. It doesn't alter any thing, or it doesn't alter any way to the stack. Okay, it just returns. It also checks the underflow condition. That means if there are no elements, then it will simply return. Okay, and then I have written the int min. So you can return anything. For example, you might return 100 or 1000 or 10,000, basically just to define that if I'm getting 1000 as a returned value, right? So that means there are no elements. You can return anything right there. So after that, then we have this return stack. That means please get me whatever is in the top of the stack without altering the stack. Okay, just give me the last element. That's it. Now let's talk about the main function, right? So here we have created a array which is of 100, right, which is of size 100. Then we push into our stack 10, 20 and 30, sorry, 10, 20 and 20, right? Then we try to pop the element. So whatever is at the last, 20 will be popped. Again we are popping, so again 20 will be popped. Then we check if the stack is empty. Is our stack empty? No, there is 10 present in our stack, right? So that's what I have printed in the output section. So it is printing not empty. Okay, this is how we do it. So now let's talk about that bonus question. Okay, what is the bonus question regarding stack? So have you guys heard about postfix evaluation? This is the classic example wherein we can use stack, right? So what happens in the postfix expression? I will show you. Just give it a try. For example, postfix expression works in a fashion that the operators are written at the last. For example, if I wrote 2, 3, 2, 3 and plus, so that this means that this is if we convert it to an infix expression, that means it will be 2 plus 3, but in postfix it will be written as 2, 3 and plus. So the operators will be at the last. Okay, so pause your video and give it a try. So I have written here the postfix expression, right? Please find the postfix evaluation of this expression. 231 multiply sign plus 9 and minus sign. Okay, so how would we use a stack here? So basically how we gonna use this, please give it a try. I'm just discussing the algorithm. So right, you have to find a way to solve this yourself. Okay, I'm just explaining a little bit so that you get the idea, so that you can implement your these data structures. It's all about learning, right? So what we are going to do here, first, whenever we see an operator, we will execute the pop operation. Okay, whenever we see the operands, right, 2, we are going to push it in the stack. So I'm going to just write stack down here. Okay, so we saw 2, push it in the stack. Okay, 2 is in the stack. We saw 3, push it in the stack. We saw 1, push it in the stack. Now we saw an operator multiply. What we will do, we will since all these operations are binary, so we need two operands, right? So we are going to pop 1 and 3, right? And just check, we can use a switch here for checking. If it's multiply, then we multiply. If it's addition, then we add them. If it's negative sign, or if it's minus sign, then we subtract those elements. Okay, so similarly for mod and other those things, keep it simple. Okay, so now we saw a multiply sign, so we will just multiply 3 into 1, right? We get the output, and we will just push that output again into a stack, which is 3. So 3 is in the stack. Now what we saw another operator, right? We are going to pop both these elements 2 and 3 and add them. Both of these are popped, add them, and then the output is 5. Again insert them into the stack. Then we saw 9, right? We saw 9 and we're going to push it in the stack. Then we saw the subtraction operator, the minus sign. Then we are going to again pop these elements and do a subtraction here. So whatever we popped, 9 and then 5. So 5 minus 9 will be -4. Your answer should be -4. Okay, got the gist? Please give it a try.
So now let's talk about queue. So queue is also a linear data structure like arrays, stacks, and linked list. So it follows a FIFO manner while inserting or deleting an element. What do you mean by that? First in, first out. If you have observed, when we stand in a ticket counter to buy tickets for a movie or a bus, we stand in a line. What is that line? Whenever a new person comes, he goes from the rear side, right? And whenever a person buys his ticket, then he removes from the front of the queue or front of the line, right? So in the similar fashion, queue also works. Okay, whenever the insertion takes place, it takes place from the rear end, and deletion takes place from the front end, right? So there are some major operations that we do in a queue. Those are enqueue, dequeue, peak first, and peak last. What do you mean by these operations? Enqueue, it means to insert an element at top, right? We are inserting an element. Then we have dequeue, we are removing the element. Peak first, we are peaking the first element, and peak last to get the last element of the queue. So all these operations are done in a constant time, that is big O of 1. How? If you think about this queue linear data structure, you might think that we have two pointers, right? One for the front side and one for the rear side. So if we are inserting, we know the last point of both these pointers, right? If we insert an element, we have the pointer, that is rear pointer, help us out, right? So we use that pointer to insert an element for last. And similarly, to delete a element, we have the front, right? So we delete from the front side. So all these pointers helps us to make this queue data structure and all these operation in queue data structure to work in a constant time. Now let's talk about disadvantages and advantages. So what are the advantages? The advantages is quite similar to what we have. It follows a FIFO manner. Insertion and deletion takes place in order one time. These are some advantages. What are the disadvantages? Manipulation is restricted, as we see that we only can insert from rear side and delete from front side. So the restriction is there, right? Not much flexible, you see. What are the applications? Scheduling algorithms, right? CPU scheduling, disk scheduling, breadth search. These are some applications. Maintaining a playlist is another application. And finally, we have interrupt handling. If you have some idea about how operating system works, if there is an input and output buffer, right? We have a IO buffer. Sometimes an interrupt comes that has much more priority than what we are executing. Do we have to remove that process and shift it in a queue to execute the process which is having much priority than what we are executing, right? So then that process will finish its execution, then whatever is in the queue goes into the execution. So you see, therein we need a queue. Okay, now let's see the demonstration. So we are implementing our queue data structure using arrays. Similarly, you can do with the help of linked list. Again, you have a small assignment. It's not about just watching this video and not learning anything. You have to solve these problems, right? If you don't face a problem, that means you are not learning, right? So I'm giving you these assignments so that you can think yourself. Maybe you are stuck somewhere. That is what makes it this interesting, right? So that's how you learn, by stucking, by watching something, by watching some more videos. So yes, you see, this is how we learn. So I'm implementing this using arrays. Similarly, you can do it using linked list. So let's go through the skeleton quickly. So the structure we are using here contains 3 elements, right? First we have front, rear and size. Okay, then we have unsigned capacity, and then we have an integer array. So what do you mean by this unsigned capacity, right? In linked list you don't need this because therein the size is dynamic, but since we are using arrays, we have to define a size. So that's why unsigned capacity. Now let's go to the how we create a queue. So basically it is returning a queue, right? So we need a pointer, right? And its argument is unsigned capacity, so that we can assign it to the size of the array, right? In the second last statement, if you can see, we are using malloc function to assign memory to the array, right? We are typecasting it to an int. Let's go to the third line from the last. So we are then assigning the rear the capacity size -1. Since we are using arrays, indexing starts from 0. Then front and the size are 0 because we don't have any elements right now in the queue, so they are pointing to 0. Then we have capacity. The queue capacity is equal to the capacity of the array, right? Therein we can store only that much elements in the queue which are present in the array size, right? The size defines the capacity of the queue. Then we are allocating memory to the queue, okay, in the first step. Now let's check out some operations that we are doing, okay? Enqueue, dequeue, and then also we are checking the underflow and overflow conditions, right, in the queue. So the first operation that we are doing is full, right? It checks the the overflow conditions, right? So then we have how we add an item in a queue. First we check if the queue is full, then we can't add an element, right? Then after that, if we are done with this and we can insert an element in the queue, then what we did here, you can just forget about this line for now, wherein I'm using modulus operator. So let's check about the other statements that are present in this function. Okay, first we insert element in an array, then we increment the size, right? And then we print that element that we have inserted this element in the queue, enqueue to queue item. Then we are printing this item, right? So what have I done here by using a modulus operator? You see, we have a pointer which is pointing to the rear side, right, which is used for inserting an element. So what we did, we inserted the element in and inserted up to the last, right, the capacity size -1. So you see all the elements are there, 1 2 3 4 5 6 7 8 9 10. For example, the size of the array is 10, the capacity is 10, right? We have inserted all those elements. Now what with the help of front pointer, we are removing all those elements and we are at the last element. So you see, now if I'm trying to insert any element, I can't, right? But there is a capacity, right? 9 elements are left which are not assigned to anyone, right? The 9 indexes, the 9 elements are present there, but I can't assign it. So modulus operator helps me in assigning values to those empty elements also of the array, okay? So that's why I'm using this modulus operator. Then there is a function that is empty to check if the queue is empty or not, okay? Then we dequeue. That is the last element, the last operation that we are doing is dequeue, right? Removing element from the queue. So first we check if is empty, is false, that is there are elements in the queue, only then we can remove, right? The underflow condition. If the queue is empty, then we are trying to remove something, we can't, right? So this is the underflow condition that we are checking first. Then we are removing from the front size again in the similar fashion, so that if somehow we have done whatever we taught earlier, right? I told you that if we are deleting all the elements, then we are present, then my front and rear are the same position, so I can't remove anything, right? Because the last element is removed. So after that, what happens? And I have inserted all those elements, but my front is pointing to this, so modulus operator helps me to remove all those elements in the similar fashion. Then we decrement the size of the queue, then return the item that has been removed. Now let's see the front and the rear side, how we use those things. So basically the front, if we try to get the first element, we just print out whatever is in the front, right? We just return that element, and to get the last element, we just return whatever is at the rear side. Okay, this is the main function, that at that time we are just inserting few elements in the queue, 10, 20, 30, 40, and then we dequeued one element. What will be dequeued? 10, right? And then we say what is the front element, then it will be 20, and what is the rear element, it will be 40. Right, this is the output of the program that we just saw. Okay, now let's talk about binary tree. This is the most important data structure that we are going to study, right? It is not a linear data structure like arrays, linked lists, stacks, and queue. It is a hierarchical data structure, right? In that it means if we are doing something, that there is a parent, there is a child, then there are sub parents and sub childs. Every node is connected to the topmost node in somehow. Okay, but it's a binary tree, so at most there can be two children of a parent, right? Every node can have at most two children, right? We are talking about binary tree, right? The topmost element is known as the root of the tree, right? Can we access randomly using index? Yes, we can access elements randomly using its index. For example, if we have seen a file system, right? If we are talking about any file system, there's a root folder at top, then we have processes, libraries, and all those are connected to that root element, right? Some common traversals we are going to study in this lecture, okay? That is pre-order, post-order, and in-order. So basically, what do you mean by pre-order? So if we talk about a tree, therein we have two children at most. So first, the pre-order, it first prints that node, then it goes to the left side. Okay, then it prints that node, then goes to the left side recursively, right? Then it prints again, then it goes to the left. Unless and until it has no left, then it goes to the right. Okay, print left and then right. Okay, similarly, the post order works in such a fashion that it goes to the left, left, left. Unless there is no left, then it goes to the right. If there is no right, then it prints that right element. Okay, we will see one example. In order works, it first goes to the left, then prints that, then goes to the right. Okay, now let's see how these works. First, we will talk about some advantages and disadvantages. So the advantage is that we can represent data with some relationship, right? There is a relationship between nodes, right? There is a relationship. Insertion and if we're trying to insert or search an element, it is much more efficient. Okay. Now, what are the disadvantages? The sorting is very difficult if we try to sort these binary trees. Okay. Not much flexible. We will talk about it in this session as well. Some binary trees which are much more flexible than binary tree. What are its applications? There are multiple variations to the binary tree, like we have BST, we have AVL tree, we have red-black tree. All those are variations of binary tree, right? What are the other applications? File system hierarchy is another application which uses the same structure. Okay, now let's see its demonstration. The node that we are using, the skeleton for tree, we are using that it contains three elements, right? The left pointer, the right pointer, and the data. So how we create a tree? First, we allocate memory to a tree with the help of malloc. Okay, how we assign our data is similar to what we have been doing, right? We go to the nodes data part and we assign the data. Then we have left child and the right child, that is the left pointer and the right pointer. At now they are null, and then we finally return the node. Okay, this is how we create a tree. Then we talk about traversals. So we are using recursively. You can give it a try to solve it in a non-recursive fashion, right? In recursion, we are using stack internally, right? We know that. So we can avoid that stack by iterating with the help of loops, right? We can use some other things to without recursion, right? We have to try that out. Okay. So now let's talk about traversals. Okay, so herein we have used three traversals, right? Post order, pre-order and in order. So let's talk about post order. So post means that we are printing our elements at the end. So if we check this function, right, herein we have used first the statement that node is equivalent to null, right? Then return. So basically if there is no node in the binary tree, so what are we going to traverse, right? And this also is our base condition for the recursion that we are using. Okay, if there is no element on either side of the left or the right child, then we return. Okay, so then first we go to the left side, then to the right side, and then we print our data. So how does this work? Basically, if we have 4 elements, 1, 2 and 3 and 4 elements, right? We have 4 elements and they are built in such a way that 1 is the root element and 2 and 3 are its child. That 2 is the left child and 3 is the right child, and 2's left child is 4. Okay, so we have this tree, right? So I am passing you the head node, right? So the node head is present. So herein we have 3 function calls, right? Left, right and print statement. These are the 3 statements we are going to execute, right? So we check if left subnode is present. Yes, it is present. Then we go on the left child, that is we are present on 2, which is the left subchild. Okay, then again it is having 3 statements. What? Left, right and print. 3 statements are present. Then again the function call goes to the left side, right? So on 4, now we are in 4, right? So now we are at 4. So again it is having 3 statements, left, right and print. So now we are going to the left again, but in the left it is null. So our node is equivalent to null. So we return from here. Okay. Now on 4 we check if there is a right child. No, there is not. So return will help us again and it will return the control. Okay, and then finally we are going to print. So in the given binary tree that I just told you, first element in post order that will be printed is 4. Okay, and then we have covered the left child of the 2. Then we go on the right side. Since there are no right childs on the 2, so we come back and print the 2. So the other element that is going to be print is 2. So after that, now we are present at the 1, that is the root node. So left side is covered. Then we go on the right side. When we go on the right side, we are at 3. So 3 left is null, right is null. Then we print the statement, right? Print statement is there. So we print 3. Then finally it will come back and print the root node, which is 1. So if the tree that you have written and I have told you, so if the tree is 1 and its root node is 1 and its left and right child are 2 and 3 and the 2's left child is 4, if we are drawing this tree, then the post order of this tree will be 4, 2, 3, 1. Now let's talk about in order, right? So in order, if you see this function carefully, only the print statement is changed, rest is same. Now we first traverse to the left side, then print our statement and then print our nodes data, and then we go to the right side. So these are the 3 statements, L, P and R. What do you mean by L? Go to the left side, P means print and R means go to the right side. So similar tree we are drawing for this as well, trying to debug this. Okay, 1, 2 and 3, then we have 4. Okay, so similarly root node is 1, then 1's left child is 2 and right child is 3 and 2's left child is 4. Okay, now let's see. First, we are at the root node and it's having three statements L, P and R. Okay, so it goes to the left side, right? Now it's also having L, P and R. We are at 2, so it goes again to the left side. Okay, then we are at 4 and it's also having three statements, right? Left, print and right. So when we are at 4, it goes to the left, it checks its null and then it returns. Then we print. So print, we are printing 4 first in order traversal. Then it goes to the right side, it is null, it comes back. Then it goes back to its parent, which is 2. So 2's second statement is pending, so it will print. So the second element will be 2. 4 and 2 are printed. Then it goes to the right, there are no elements in the right, then it goes to its parent, which is the root node, that is 1. So left side is covered, then we print 1. And then finally we are at the right side and the 3 will be printed. So in this case 4, 2, 1, 3 will be the output of this tree. Now let's talk about pre-order. So similarly, only the statement that is changing is the print statement. So we first print our element, then we go to the left, then we go to the right. Now same tree we are drawing 1, 2 and 3 with 4, with 1 as the root node, 2 is left child and 3 its right child, and 2's left child is 4. Okay, now let's try to debug this as well. So first 1 will be printed because print, left and right are the statements that we are going to execute. So print is done, then we move to the left. So then we move to the left, then print is done, that means 2 will be printed, then 4 will be printed and then 3 will be printed. So the output of this will be 1, 2, 4, 3 if we're talking about pre-order. So you see 1, 2, 4, 3 is of pre-order, 4, 2, 1, 3 is of post order, 4, 2, 3, 1 is of post order, and for in order it is 4, 2, 1, 3. So this is the main function that we are going to run for this program. So you see herein we have a root, then we created the first node, then we second node and the third node and the fourth node, then we executed all those statements, all those functions. We try to execute those functions, right? Pre-order this, then in order this, then finally the post order functions. So you can do it on yourself. It is again a little assignment for you guys. You can just change the nodes or insert some more nodes and try to figure out what is the pre-order and post order. Then you will execute that code and check if you're doing it in the right way. Okay, now let's talk about BST, binary search tree. We have given binary tree and additional responsibilities and restrictions. Okay, what do you mean by that? We are building a tree in such a fashion that elements to the left side of the root node are less than the root node. Okay, if we're talking if 4 is the root node, then the only child which will be present on its left side, that means I'm talking about the left childs, will be less than 4, and all the elements which are present on the right side will be, that is the right childs, will be greater than 4. And this is true for every sub node. Okay, every child, this is true. For example, if I'm talking about left node, the left node's left will be lesser than the root node, that is the parent node right now, will be less than that, and all the elements which are greater will be greater than that. So the left child must always be less than the root node for every node I'm talking about. Okay, and similarly the right child must always be greater than the root node. Insertion, deletion and search operation, if we're trying to do these operations, are much more efficient than binary tree. Now let's talk about some advantages and disadvantages. So it maintains order in elements, right? You see, if we're trying to insert elements in a binary search tree in such a fashion that it maintains some order and can easily find a min and max nodes in the tree, right? We can easily find minimum element and maximum element, right? In order traversal gives you sorted elements. This is the most important line if we talk about binary search tree, wherein the in order traversal gives you sorted elements. We are going to solve many questions with the help of this statement. I'm going to give you one bonus question as well in the end of this binary search tree, wherein we are going to use this statement. What are the disadvantages of BST? Random access is not possible. Similarly, as we talked about binary tree, in that also random access was not possible. Ordering adds complexity. Since we are adding some responsibilities, it adds to its complexity. What are some applications? It is suitable for sorted hierarchical data. Now let's see the demonstration of BST. So similarly, there will be a key and the left child and the right child. The key here is the data. Okay. So first, now we are trying to create a BST. So first we have the item as its argument and we are returning the node. First we assign memory to the node, right? Then we insert value in it, the item. Then we assign the left child and the right child as null. So what is the in-order traversal? It is same as in what we did in binary tree. Okay. So this is the demonstration of now how we going to insert and the main function. So how we going to insert? So every time if an element is less than its parent node or any node, it is going to be inserted on the left side. And if it's greater than, then we are going to insert it on the right side. So these calls to the insert function, we are again using recursion. If you want to study about recursion, you must study about these trees, because every time if you're facing any competitive programming questions regarding binary trees, you always are going to use recursion. Okay, so it really helps. So we are calling every time the insert function again and again. So if you can see carefully, we are again using a base condition wherein we check if the node is null, then return, right? So this is the code for insertion, and the main function, in the main function we are just inserting 50, 30, 20, and it will be ordered similarly. Will be an order maintained to it. Okay, what order? We have already studied that. So this is the output of this program. So this is the output when we try to find in order traversal on these elements which we inserted. What will be the answer? If you can give me any guesses. If you told it will be in sorted order, then you are right. Absolutely. You see 20, 30, 40, 50, 60, 70 and 80. This is the output because we are using an in order traversal. Okay. So now it's time for the bonus question. Let's say you are given a binary tree or you are given a BST and you have to check if it's a valid BST or not. What are you going to do? Give it a try, pause the video, give it a try to solve this or try to think. You have to check if this tree is a balanced BST. That is, if this tree is a balanced binary tree, that is, if this tree is binary search tree or not, a valid binary search tree or not. If you said you are going to use in order traversal, then you are correct. In this question, we are just going to implement a in order traversal. If the output comes to be sorted, then this tree is a valid BST. Okay. This is most simple application or most simple program that one can think of, right? This is very important that every time if you try to traverse in an in-order fashion in a BST, it will always give you an output in a sorted manner. Okay. So now let's talk about heap data structure. Basically, we are going to represent heaps as an array, but we will visualize it like a complete binary tree. What do you mean by a complete binary tree? Basically, a complete binary tree is a tree wherein every node has two children except the leaf nodes, and in the leaf nodes the elements are filled from left to right, such that we can represent it in the form of array, wherein the element present at 0th index will be treated as a root node. Okay, so this is how we're going to implement binary heap. We are going to visualize it like a complete binary tree, and we are going to store elements in the form of array. Length of the array is represented by length A, and heap size is represented by heap size of an array. Okay. Generally, when we are dealing with minimum and maximum elements, we go with heaps. So if we talk about heaps, we generally have two variations, a min heap and a max heap. Basically, in min heap, root node is always less than its child, or parent node is always less than its children, and it will follow for every node in the heap. Similarly, if we talk about max heap, in max heap, root element or parent element will always be higher than its child, and it will also follow for all the nodes in that heap. Okay, so what is written in this chart? The parent I minus 1 divided by 2. What does this mean? Basically, when we represent our nodes in the form of array, so if we talk about any particular index, for example 3, I'm talking about this third element, which elements are going to be its left child and which element is going to be its right child. How are we going to find it out? Basically, if the index of this third element is 2, so we multiply 2 by the index 2, that is 4. 4 plus 1, 5. So fifth indexed element will be its left child. And when we multiply it by 2 plus 2, so 2 into 2, that is 4, plus 6 plus 2, that is 6. So the element at 6th index will be its right child. Can we find out for a particular index or for a particular node who is its parent? Yes, we can. For example, if the element at index 2, we have to find its parent, right? We know it's 0, but how are we going to calculate it? First, we will do 2 minus 1, right? 2 minus 1 is 1. 1 divided by 2, basically we are doing here integer divided by integer. So 1 divided by 2 is 0.5, which is 0. So 0th element will be its parent, which is true. Similarly, we can find it out for rest of the elements. So this chart is very important. We are going to use this chart in the rest of this, and we are going to follow this structure, okay, this chart. Let's now talk about some advantages and disadvantages. Can be of two types. We know min heap and max heap. Min heap keeps the smallest element and the max heap keeps the largest, which is present at the top, right? That means if we're talking about max heap, the element present as 0th index will be the maximum element in the whole heap, okay? Similarly, if we talk about min heap, the minimum element will be present at the top. So when we are trying to find out minimum element and maximum element, we can easily find it in a constant time, right? So the time complexity for removing the top element or finding out which is maximum or which is minimum is order of 1. For insertion and deletion, if we talk about these operations, the time complexity is of log n, which is depth of the tree or depth of the heap, okay? So how it is log n? Basically, if we're trying to remove the element which is present at the last, that is the last index of the array, so it can be done in order of 1 time. But what if we are trying to remove the first element, right? At that time, we will replace the first node with the last node, okay? Once we replace the array elements, let's talk about in arrays. Okay, so we will replace the 0th index with the last index, then we will swap them, then we will remove the last index. Easy, right? But now our heap has been deformed. We need to max heapify it. If I'm talking about max heap, so now we have to max heapify it. So we will bubble up and find out which is the largest element so that we can put it on the top. So for this we will need log of n time. Similarly, when we're trying to insert something, first we will insert it at the last index, then we will bubble it up and find its appropriate position so that it follows the property of max heap. So this time will also for this operation, time complexity is also of log n. What are the disadvantages? Random access is not possible, right? Only min heap and only minimum and maximum element is available for accessibility, right? So we only know that only the element which is at the top, we can access only that, and that will give us the appropriate results, since this is the only element which will be maximum. If we talk about other childs of this root node, they won't follow that property, they will be maximum in that tree or in that subtree, but they won't be the total maximum. Okay, they won't be the next maximum. For example, the root node is first maximum, then the second maximum is this, then the second maximum is this. We can't deduce that. Okay, what are this application? When we're dealing with priority, we can use heap. When you're using, we can use it while scheduling algorithms, right? Caching, we can use it in caching, right? So let's now see the demonstration. So I'm building a max heapify. Similarly, you can make some changes. It is your assignment once again to build a min heap. So let's talk about first heapify, max heapify. So we have two variables, right? Left and right. So we are using that same property, 2 into I and 2 into I plus 1. Basically, why I have changed this formula? You see, here I have written 2 into I and 2 into I plus 1, because in this case I was choosing my index 0 to be my root node, right? But herein I am using first element as in my root node, so that if I multiply 2, for example, the root node is present at 1, index 1. So which will be its left child? So 2 into 1, right? That is 2. And 2 into 1 plus 1 give me 3. So third element will be its right child. So that's why I'm changing the formula. Then we will check if it is less than the heap size, and if the left element is greater than the right than the index that we are, then the largest element is this. Then if not, then the largest element is the index. So similarly, we can find it in the other subtree. Okay. So this is how we build a max heap. So we will build it on each parent node. So you see, we are doing C by 2 in the built max heap, right? So then we max heapify that parent node. Similarly, we will do it all for all the parent nodes. Okay. Basically, why we are using this heap size and why we are using the max heapify property here. Basically, we are trying to build a max heap such that it follows the property of that the element at the top of the heap is the largest element, and element at the, or if we are talking about min heap, the element at the top of the heap is a minimum element. Okay, we are following this property. Try to dry run this code and you will get to know what exactly is happening. Basically, we are checking if this node, if the root node is less than or greater than this, then we check which one is the greatest so that we can swap those elements. Once we swap those elements, then we check the element that has been swapped, is that following the same property? If not, then we are calling the max heapify again. You see, and just above build max heap, there is a max heapify called again, because once we swap the elements, then maybe we might have deformed the max heap. That is, we might not be following the same property. So that's why we are calling for the other elements as well, which have been changed. So in this way, we will build our max heapify. Now, how can we find the element which is maximum? Simple. We will return the first element. I was telling you earlier also that I'm using my first element to be at index 1. So that's why I'm returning a of 1. In your case, if you're trying to implement it with 0, then you have to return a of 0, because that will be the only element which is maximum throughout this array. How we can extract max? So once we have extracted our maximum, then we have to change it, right? Once we have extracted our maximum element, we need to find out the other maximum so that we can replace it with that. Okay, what we will do? First, we will replace this maximum element with the last node, that is the last index. Once replaced with that, we will remove the last index. So that is our extraction of maximum element. But now we will check, is this element greater than this, greater than its left child and greater than its right child? If yes, then we will do nothing. If not, we will find out which one is the maximum between these two. right? We are calling the max heapify, you see. And we also decreasing our heap size, because we can't decrease our array size, right? We can decrease our heap size. That's why we are using heap size and array size. Array size will remain same, but in heap size we can remove it, since we are not dealing with 9 elements or 10 elements now, because we have extracted one element, so our heap size is decreased. Now we are calling max heapify function again, so that we can check, does this once removed, does this follow the same max heapify property or not? So we will find out the maximum between these two with the help of max heapify, right? Earlier explained, right? So that's why first we will check it with the left, then the right, and then once we have found the largest, if that is the largest which we had already, then we make no changes. If not, then we will make the changes and replace that maximum element with the root node. Once done that, then we will check if this is the property that is following, this node that we have changed, is this element also following the same property or not? If not, we will again call max heapify on it. Similarly, once all these elements follow this property, only then we can be sure that this heap is following a property of max heapify. That is, the root node or the parent node is always greater than its children, right? So this is how we do it. Now we will see the main function. Herein we have declared an array, heap size, then we are calling build max heap, then we are finding the maximum value, we are printing that value, right? Which one will be the maximum? Maximum will be 16 here, right? So maximum element is printed, we display the element of the max heap priority, right? Display the element of the max heap priority, then we call the function and extract maximum, right? These are the steps we are doing in this program, okay? What will be the output? The output will be the maximum element is 16, right? Then we are displaying the heap priority. That's 16, 14, 10, 8, 7. This is the maximum numbers that we will be extracting. These are the maximum numbers in the heap, right? Then we are extracting the maximum value, that is 16. So this is how we conclude our heap topic. So now let's talk about the question or the bonus question that I try to give after completing every topic. So the question is, you have to find the largest element in an array, right? But not the first largest. The largest can be any number. If I'm talking about the first largest, the second largest, the third largest, you have to give me that largest number. For example, in an array, in this array right now shown on the screen, you have to give me the fourth largest number. Okay, what will be the fourth largest number? 16 is the first, 14th is the 10th, then 10 is the third, and 9 is the fourth. So fourth will be the fourth largest element is 9. So you have to give me this number. So the first approach that you might be thinking, and which is very intuitive, that you will sort this array and you will just give me the element present and the fourth index, but the time complexity is much high, right? So the second approach is, and by far better than this, is using a heap. You can easily create a max heap, and you will just remove the first element from it, then the second and the third and then the fourth. The fourth element will be a 9. So try to implement this, okay? Use max heapify, use the same approach that we are using here. Try to build a max heapify, then extract max 4 times, call this function 4 times, and basically it depends on which element you are trying to extract. For example, here I'm talking about fourth element. I might be saying that the kth element, you have to give me the kth element. That means if I will give you k equal to 5, you have to give me the fifth element. So that many times we will call our extract max function. Okay, so let's conclude this topic here and let's move ahead with the next topic.
So now let's talk about hashing. Basically, hashing is not a data structure, rather it's a technique which we use to implement our data structure, that is hash table. So now let's talk, before talking about hash tables, let's talk about this hashing. Basically, in hashing we use a special function called hash function, which we use to map our elements to a particular address for storage. For example, if we are using a hash function, say x modulus 10, right? So what is x? X is an element, right? X is an element here on which we do an operation of modulus. We do a modulus operation, that is modulus by 10. So what will be the remainder? Remainder will be 0. So we will try to implement this technique. So how are we going to implement this technique? Depends on the data we have. So for example, let's suppose we have 10 elements, 121, 145, 132 and so on to 999. We will try to mod it by 10. So how many spaces we are going to have in a hash table, right? If we try to do modulus by 10, so what will be the remainder? What will be the possible remainders, right? It will be from 0 to 9. So we will try to do a modulus operation to all the elements and map them to these particular locations, that is from 0 to 9, okay, with the help of this hash function. Okay, so why do we do this? Why do we need a hash function? Basically, hash function helps us to search an element in a constant time. Also, we can perform deletions in a constant time. So while we modulus anything by 10, for example, we use a modulus operator on 121. When we do a mod operator on 121, that is 121 mod 10, what will be the remainder? 1. So we will map this 1 to index 1. Okay, so the element that 132, right, we will try to get with the help of this hash function. We will try to map this element to address for the storage. So basically what we do, we will get this 2 and map this to that in the array thing that we got, that is from 0 to 9. We will map this. So let's suppose we have 10, 20, 30, 40, 50, 60. So all these elements will be mapped to a particular location, that is only one location, right? Because when we mod them by 10, all of these elements will give a 0 remainder, right? So we are trying to map these elements to a single location. So during this time, there is a collision, right? What do you mean by collision? When we are trying to map one or more elements to a particular location, so there is a collision. So this collision, how are we going to handle this? Basically, we have a resolution techniques for this. Basically, the first technique is try to build a better hash function so that we can minimize these collisions. But this hash function, every time when a person is trying to build a hash function, why will he build a hash function which is not suitable, right? So this approach is quite arbitrary, right? So try to build a better hash function. Now, what are the two main techniques of resolution with which we can minimize our collision? So the first one is chaining. What do you mean by chaining? Basically, whenever a collision happens, for example, 10, 20, 30, 40, so there's a collision. We are trying to map 4 elements to a particular location, right? So now, in chaining, what happens? Basically, a linked list is created. So in 0's position, we try to build a linked list. So 10 will be linked to 20, will be linked to 20, will be linked to 30, 30 will be linked to 40. So if we are having elements that is 10, 20, 30, 40, 50, 60, so all of these elements will be linked to a particular location, that is 0. With the help of a linked list, we will link all these elements in that particular address, right? On the address where we have written 0, right? So this technique is called chaining. We are using a linked list. Okay, but is this technique efficient? No. Why? If we are trying to implement 10, 20, if we are having elements 10, 20, 30, 40, 50, 60, so all of these elements will be mapped to a particular location using a linked list. But when we are trying to find any element, let's talk about in worst case, if our element is at the end of the list, so how much time do we take to access that element? Linear time, right? That is not the point, right? We are trying to access elements in a constant time. Can we do that with the help of chaining? I'm talking about worst case. No. So this is one of the techniques, but it doesn't solve our problem. Maybe in some cases it might solve, but right now the example that I am giving, it's not solving. So there is another technique called open addressing. Whichever address is open, try to access or try to insert element at this position. So in open addressing, we have three techniques, three types, right? Linear probing, quadratic probing, and double hashing. What do you mean by linear probing? So basically, what do you mean by probing? Probing means searching, okay? So in linear probing, what happens? We are trying to build a hash function wherein we add collisions. What do you mean by this thing? Basically, we right now, if we're talking about earlier case, we were using a hash function of x modulus 10. Now what we will use x plus I modulus 10, where I represents the ith collision. For example, now we have the first element 10. I insert it in the 0th location, right? So next time 20 comes. Now the collision this time happens. Now this time the first collision happens. So it will be 20 plus 1. The first collision is happening. So 21 mod 10. So our output will be 1. Rather than 0, our output will be 1. So what we did, we just shifted it to the next location, okay? So if there is an element, then we shift it again. So open addressing, whichever address is open, we try to insert our element in that location. So how this is helping us or helping our cause? So basically, if next time 30 comes, let's suppose 10 is inserted at 0th location, 20 is inserted at first location. Next time 30 comes, so it will be the second collision. So 30 plus 2 mod 10, what will be the result? 2. So it will be mapped to second location. Now what happens here? Basically, if in this chaining method, there is one problem associated with it. We have seen that, right? In open addressing, we are talking now about linear probing. Now there is also a problem. What problem? Basically, if I am having elements 10, 20, 30, 40, 50, 60, all these elements will be inserted in locations like 0, 1, 2, 3, 4. Okay. Now, if we are having 10 to 40 elements, now if I am having 55, 65, 75, 85, right? These also will be mapped to 5, 6, 7, 8. So basically, if I am talking about a larger picture wherein I am doing modulus by 100, if I see a broader picture, there will be memory chunks, right? So there will be a memory chunk of 0, which will give me the output of 0. There will be memory chunks of elements which will give me the result as 5. Then I increment them with the help of this ith collision, right? X plus I mod 100, which I'm doing right now. So there will be memory chunks available. There will be no proper distribution of elements, right? So to do a proper distribution of these elements in open addressing, we have another technique called quadratic probing, okay? Wherein the hash function which we use is x plus I square mod 100 or mod 10. So with the help of this technique, we are trying to distribute our elements in such a way that there are no memory chunks that we are using. So we are trying to distribute our elements evenly. This is another technique in open addressing. For example, now in this case, what happens if 10 is present at 0th location? Now 20 comes. So it is the first collision. So it will be mapped to 1. But if 30 comes, it is the second collision. So 30 plus I square, it is second collision. So I square is 2 square is 4. Alright. So the result will be 4. So you see, instead of 0, 1, 2, we are inserting it into a location or mapping it to an address wherein we are using 0, 1 and then 4. So we are distributing it. We are trying to distribute it evenly. So there is one more problem. In this open addressing technique, that is quadratic probing, we are not able to distribute that much, right? So if we try to implement some example wherein we see even this is not distributing evenly. So the final technique that we are using for the resolution of our collision in open addressing, we have double hashing. Basically, in double hashing, what do we use? We use two hash functions, okay, wherein we use first hash function plus the ith collision into second hash function. So this is the techniques, these are the techniques that we use to avoid collision or to minimize collision, and also keeping in mind that we are evenly distributing our elements. Okay, so let's talk about now advantages and disadvantages. So what are the advantages? Hash function helps in fetching element in a constant time. Okay, with the help of hash function we are able to fetch elements in a constant time. It's an efficient way to store elements, as we have seen all the techniques, right? What are the disadvantages? We need to increase complexity. Why? Because of these collisions, right? We have to find a way to avoid or minimize these collisions. So this is the disadvantage that we have with hashing. What is it suitable for, or what are its application? Its application is when we need a constant time to fetch an element or to delete an element. Okay, these are some advantages and disadvantages. Okay, now let's try to implement this hash table. Now with the help of hash function we are trying to implement our hash table. So we define an item, right? We are defining an item here, structure item. Whenever we talk about hash tables, we have to keep in mind that we have one key and we have data. So with the help of that key we will fetch our data. So that's why we are having two elements in this, data and key. Then also we have to define a hash array size, right? This size is the operator that we are using, right? That every time when I said that modulus by 10, modulus by 20, so this size represents that thing. Okay, then we are also having an item that is, we are using a dummy item wherein I will show you where to use this dummy item. Okay, so let's talk now about hash function or hash code which we get. So here we are using, for simplicity, we are using a simple hash function wherein we get a value, we mod it by the size, right? Similar to what I was explaining to you earlier. Okay, so let's talk about now how to search an element. Okay, in a hash table. For example, in a hash table we have 5 elements and the keys are 1 2 3 4 and the elements are 10 20 30 40. Okay, this is the hash table that we have. How do we find an element? So basically, for how we inserted an element into this hash table, using a hash code, right? Using a hashing function. So similarly we will use the same function, hash code function, wherein we try to search an element. So that's why the first line in this search function is we are calling the function hash code function to get the hash value. So once we got the hash value, we will check if this is present in our hash table. Okay, if it's not, then we will return null because it's not present in our hash table. So how are we going to search it? Then what we will do, we will, with the help of key, we will check if the element that I got, the element that I got, its key is equal to the element which I have in the hash table. Are these keys equal? If yes, then we return a hash value. Okay, then we return a hash value, we return that element, and similarly we will do some operations like incrementing our hash value and checking if the hash value mod size, we are, with the help of this, if there is a collision, we will try to resolve that as well. We will try to find a solution to that as well. Okay, this is how we search an element in a hash function. Now let's talk about how we're going to insert an element. So first we declare an item, that is the dummy item that is the item that we are going to use in this when we are trying to implement hash table, or when we are trying to insert element into it, we need a data part and a key part. So when I'm calling this insert function, I am sending from the main, I will be sending both these values, right? You see here, insert, the key is 1 and 20 is the value. So I'm trying to insert these values into our hash table. So first I allocate memory, then I assign these values to it, then I find a hash code, right, with the help of which I will map it to some particular address. Then I check if it's already present in that element, or if it's already present in hash table, then what will I do? I will just move along. Okay, then if it's not present in the hash table and its key is -1, right? If it's not present and its key is -1, okay, I will increment our hash value which I have found with the help of this hash code. I will increment that and I will insert my element into this hash table. Okay, this is how we do an insertion. You see, in the while I have used two conditions. First, wherein I am checking that this should be not null, that is the hash value that I got, this should not be present already in it, and the second, that if its key is equal to -1. So you got the point, right? How we're trying to insert elements into the hash table. So secondly, when we are trying to delete an element, first we have to check if the element is present in that hash table or not. If it's not, then we return null. If it is present, then what we will do, we will first find the hash code and then we will try to check where it is. So with the help of key, we will check if this key and the key which we got are similar, then we will define and we will allocate memory, or we will define a temporary variable, temporary pointer, wherein we store the element which we have to delete in that, and then we return that element so that that can be print that we have deleted this element, right? In such a way we will define our insertion function and deletion function, and earlier what we studied, that was how we search an element in the hash table. So in this way we have implemented all the three functions: search, delete and insert. So now let's talk about the main function. Main function, we are first allocating memory, then to a dummy variable, right? Dummy item. So in that dummy item we are defining that the data is -1 and the key is -1. Okay, then we have called insert function several times. Then we have tried to search an element 37. Is it present in the hash table? Yes, it is. So we are checking if the item is not equal to null. So if we got a function, right? Let me show you first the search function, what it returns. If the element is not present, then it will return null, and if the element is present, then it will return that element. So in the item, what do we have? We have 37. So item is not equal to null. So what we will print element found and the item's data. Okay, we will in the item we will get the address part, right? We here return temp. So in this temp we will be having address. So address is not equal to null, that means we have the element. So whatever we got the address, for example if we got 1000 address, please tell me what is the data at that address. So this is how we are going to implement our this function, search function, and we are trying to print that element. Okay, so if we didn't find our element, then what we will print? Element not found. Then we are trying to call the function delete item. Okay, so we are deleting the item. Then we are again searching for 37, right? We have deleted it. First we searched for 37, we got the 37 element, we printed it, and then we deleted that item. Then we searched again for it. What will be the result? That element will not be found. Okay, this is why we are having two statements. That is, one, the element found is 97. Okay, yes, this is 37 is the key and 97 is the element, so the data part is 97. So that's why what we have here, element found 97 and element not found, because once we got the element here, when we first called the search function, we got the element 97, we printed it, right? Then we deleted that item, right? So next time when we called for the same function, for the same key 37, the third element is not present, so that's why element is not found comes second time. So this is how we implement our hash table. Okay, please guys, try to implement these, because this is the most important data structure. If we are talking about time complexity and competitive programming, this hash table plays a major role in that. Now let me give you a simple example, or wherein we can use this hash table. For example, if you have to find the frequencies of all the elements in an array, right? You have to find the frequency. For example, there are 10, 20, 30, 40, 50, 60, 70. Then these elements are repeated. Okay, so let's talk let me give you a simpler example. So for example, if you are having an array in which we have 1 1 2 2 3 3 3, then 4, then 5, you have to build an array in such a way that you have to, if I'm giving you an element, you have to tell me what is the frequency of this element. If it is even present in that array, you have to also tell me that. So easily we can implement a hash table, right? We can implement a hash table, for example, 1 and its frequency, 2 and its frequency, 3 and its frequency. So whenever I will give you an element, say let's suppose 1, you will check if that key is present in your hash table. If yes, you will return me the frequency, right, the data part. So if I'm giving you, so let's suppose 100 and it's not present in your hash table, what you will give me, what will be the output at that time? There is no such element found, or for example, the frequency of this element is 0 since it is not present in our hash table. So easily with the help of this data structures, this problem of finding out the frequency got very simple, right? This is the most important data structure in terms of competitive programming. So try to implement this. Okay,
so now let's talk about graphs. So graph is also a non-linear data structure like trees. Basically, a graph contains nodes, also called as vertices, and edges to connect them. A graph is represented in the form G, V, E, where VG represents the set of vertices and EG represents the set of edges. Basically, a graph is used to define a relationship between arbitrary objects or arbitrary data. A graph can be directed or undirected. What do you mean by that? A graph which contains arrows is called a directed graph, and in which where there are no arrows is called an undirected graph. When we talk about adjacency lists and matrices, there we get to know the big difference between how to make a directed graph and how to make an undirected graph. Graph can be connected or disjoint. What do you mean by this? If all the nodes are connected with each other, or if all the nodes have a edge between them, is called a connected node, and wherein a node is not connected with one node is not connected with another node. Basically, for example, if 5 nodes are present and one node is left alone and 4 of them are connected in any manner, so that will be a disjoint graph. Now let's talk about advantages and disadvantages. So a graph is used mainly because we can find the shortest path with the help of graph. A minimum cost can be reached, wherein we have to find a way wherein we have to minimize our cost from reaching from one point to another. We can easily use graphs to find the minimum cost, minimum spanning tree, shortest path. For example, if we are looking to find the shortest path between from route A to route B, we can again use graphs. To find a connectivity between objects or between data, we can use graphs. Okay, now let's talk about disadvantages. Basically, when we are trying to implement adjacency list and adjacency matrices, they can lead to complexities, because in adjacency list we are using a concept of linked list, and in adjacency matrix we are using the concept of 2D array. So basically, in this session we are going to deal with adjacency lists, but I will tell you how to make an adjacency matrix. Basically, if there are 4 nodes or 4 vertices, so basically a matrix will be made of 4 cross 4. Okay, so when we have 4 nodes, we are making a matrix of 4 cross 4. So if somehow we are having 50 nodes or 40 nodes, so you see how complicated it gets to build a matrix which is of 40 cross 40, right? And similarly, if they are directed and undirected graphs, if we are trying to build an undirected graph, therein we have to create we have to insert elements in place of those if in place of the edges for both these. For example, if we are placing up for example, there is an edge between 0 and 1, so we go into the matrix and we find out where is the location of 0 comma 1, that is 0th row and first column. We find that location and insert 1 in it if we are talking about undirected graph. So once we did that, then we also have to do the same thing for 1 comma 0, that is first row and 0th column. We have to insert 1 in it, right? So this is how we create an adjacency matrix, by going to into that particular row and column and inserting 1 for undirected. If it is a directed, then we don't have to reverse the row and column thing. Okay, so this is quite simple. So the complicated, much complicated as adjacency list, we are going to deal with that thing in this session. Okay, now let's talk about applications. It's suitable for circuit network. It's suitable for applications like Facebook, LinkedIn. It's also used in medical science. Now let's talk about how we are going to build a graph. Basically, what we are going to define two structures. One is node and another is list. In our node, we will be having vertex, right? The node. In our node, the node structure, we will be having a data which will store our data, the vertex data, right? It is represented that, for example, let's keep it simple. We are defining a node just like we defined in a linked list. Therein we have a data part and a link part. Similarly, we are defining the same node, but instead of data, I'm using V to represent a vertex. And we also define a structure, that is the list, which contains an element of head, which contains an element which is of type node. So basically, what we are trying to create here are lists. We are trying to create here a list. For example, if you can see the last line on your screen, wherein I have created an adjacency list, which is an array of type list, wherein I have explicitly defined that I am having 5 nodes and all of them are initialized with -1. So basically, I am keeping it a static. For simplicity, I'm keeping it static. Basically, if you want a variable vertices, you can easily define a macro here at top and give it some kind of a name, that is number of nodes, and you can put that thing in this instead of 5. Okay, by defining a macro. For simplicity, I have decided that I'm going to insert 5 elements, 5 lists. Okay, and I have defined the size of the array as 5. Let's go ahead and check how we're going to create an edge. First, let's go into the main so that we have a clarity. Okay, so basically in main, we are defining a loop which runs 5 times. Basically, we are allocating memory to this array list. Basically, how we are representing these things. In every the elements in the array will be of type node, and for every node, and that means, for example, if I am 5 vertices 0, 1, 2, 3, 5, okay, in that array, every node will be linked to all the nodes to which this vertex is connected. Okay, for example, if 0 is connected with 1, 2, 3 and 4, so the first element will be, for the 0th node, the head will be present here, and all the elements to which, or all the vertices to which it is connected, will be connected with the help of linked list. So we are using a concept of arrays and linked list here, wherein every head node is present in the array, and with the help of head node, we can traverse through all the nodes which are connected to a particular vertex. For example, if 0 is connected to 1, 2, 3, 4, we can traverse through this array. First, we will go into the 0th index, and then we will traverse through the linked list. So basically, here we are allocating memory for all the nodes which are present. Right now, we have 5 nodes. So we are allocating memory and putting them in the array. The next pointer of all these nodes are null. So there's a misprint in this slide. So basically, it's arrow next equal to null, and also there's a missing parenthesis in the for loop. Okay, check that out. So then once we have allocated memory, right, then we are going to add edges. Basically from there's the edge between 0 and 1, between 0 and 4, 1 and 2, 1 and 3, 1 and 4, 2 and 3, and 3 and 4. Now let's see how our add edge works. So basically add edge will take two arguments, right? The source and the destination. Okay, we have also created three temporary variables or three temporary node type of variables, wherein first, if we check if this is the first time that the source is present, then this if will execute, and if it's not, then this if will not be executed. So since this source 0 is the head part of that is null, right? The source in the array, right? Its head section is null, so we will execute this. So the first line that represents that we only insert the head in the array if it is present for the first time. So we allocate memory to that, then we assign values to it. That means the vertex and the next part becomes null, and then in the head section we will just give the value, right? The source, the 0 value will be present in the array. So similarly we will do it for all the nodes, and when the next time the 0 and 3 comes, at that time what we will do, we will allocate memory to the next portion. What do you mean by that? By destination, now 0 is present and it is connected to 1. So next time 0 comes and it is connected to 3. So how will we connect this 0? Basically we are not going to replace the array element, right? We are not going to replace the array source of the source which is present in the array. We are just going to, with the help of that, we are going to traverse through the linked list and add at the end the next node to which it is connected. Okay, so this is how we're going to do it. The while loop helps us to traverse, and then finally we will put the temporary node which we have defined here, in which we have right now we know that we can't change the head, right? Head cannot be changed of any list. So what we did, we put that head in a temporary variable, we helped it to traverse, and finally what we did, we just put the destination node on to the next of this temporary node that is connected. Okay, this is how we're going to do a graph, add an edge in a graph. Okay,
now before concluding, let's see the takeaways of this session. In this session we covered arrays and linked list. We saw their differences and their similarities, how they are similar with each other, right? We talked about stacks and queues, how they are different from each other. We talked about binary tree. Then we tried to implement the strict form of binary tree, that is binary search tree. We talked about heaps. We tried to implement max heap, right? Then we talked about hashing and implemented hash table. And then finally we covered the graphs. Thank you.